Okay, so we are going to talk about attributes of polynomials. So a polynomial is the sum or difference of many monomials. And the highest exponent of a polynomial is called the degree. And this is how you name polynomials. You name it by the degree. And you always want to put the polynomial in standard form. Okay, standard form would look like this. The highest exponent will go first. So let's say the highest exponent is a 6. Then the next one will be the 5th exponent. It goes in descending order. Do you guys know what x to the 0 is? 1. So x to the 0, this is just your constant. You also see it written as c, okay? X to the 0 is just 1, a constant. Okay, so that's standard form. It goes in decreasing order. So let's go ahead and put the first example in standard form. What is the highest degree that you see? The 5. So that term will come first. So negative k to the 5th power will go first. And the next highest exponent? 3. So then that will go next. 3k cubed. And next is the squared term. So this is plus 1/4 k squared. And your next one? Yep. 8k will go next. And finally, your constant, which is just the number, -1. So now that is in standard form. We call this a 5th degree polynomial because the highest polynomial is a 5. The highest degree is a 5. Okay? Next one, number 11. Yep, the cubed is the leading term. So I'm going to do 4a cubed. And let's just look at a being the variable here. Let a be the variable. So what's the next highest exponent? Yep, this one right here has the next highest degree for a. So I'm going to put that one next, plus 18, a squared, b squared. And the next highest exponent for a? 7. Yep, the 7ab plus 7ab. And then minus b squared, that's just your constant.
So you just ignore the b.
This is like having an a term of 0. A to the 0 is just 1. So that would be the smallest one. Okay, and we're not going to do this one. This is not a good example. Okay, because they didn't really clarify if we're treating x as the variable or y as the variable. So we'll just skip that one. Okay, so this is how you order your polynomials. Let's do some more examples. We're going to make a chart about our degrees. We're going to classify the polynomials by the degree, which is the highest exponent, and the number of terms. And guys, this is stuff you already know. If it's degree 0, it's just a constant. Any number is a constant. If the highest degree is a 1, that means it's linear. If your highest degree is a 2, that means it's quadratic. If the degree is 3, we call that cubic. Once we hit 4, we just call it 4th degree or 5th degree. Whatever number it is how you name it. This is a 5th degree. Okay, so let's just go through real quick and classify each degree. For number 13, what degree is this? What name are we going to use? Linear. This one is linear. What degree is number 14? 5th degree, the highest exponent is a 5. So this is a 5th degree. Okay, you guys get what we're doing there? All right, now let's talk about the number of terms. If you only have one term, we call that a monomial. If you have 2, do you guys know what that's called? Binomial, exactly. And 3? Trinomial. And what if we have 4 or more? Polynomial. That was a good guess. Polynomial. 4 or more. Okay, so that means this linear one for number 13, how many terms do we have? 2, so this is a linear binomial. How many terms does this 5th degree one have? 3, so this is a 5th degree trinomial. Okay, so I'm going to have you guys do the rest of the examples on your own now that you have the notes. Okay, so here are the parent functions of polynomials. A constant, f of x can just equal any number. I'm just going to put c. You can choose whatever number goes in there. Linear, f of x equals x. Quadratic, f of x equals x squared. Cubic, f of x equals x cubed. And we're going to call these just polynomials. This is a 4th degree polynomial. F of x equals x to the 4th. F of x equals x to the 5th. Okay, so what you guys are going to do is go to Desmos, type in these equations, and graph them. Sketch them on these blank graphs. So guys, for constant, you can pick any number. So example, you can pick 10. That means it's just going to be a straight line going through 10. Okay, so that's an example. Okay, so your linear one should look like this, just a straight diagonal line. Your quadratic is the U-shaped graph. Cubic, it looks like this. This 4th degree looks like this. And the 5th degree looks just like the 3rd degree, like that. Everyone got that? Nice. Let's go ahead and take some notes. So let's talk about turning points. Turning points are the points at which the polynomial function switches direction. So notice, guys, if you follow my pin, it goes from, it's increasing, and then it gets here, and then it starts decreasing. So right here is a turning point. It was increasing up until that point, and then it drops. Okay, then it's decreasing, and then right here at the bottom, it changes direction, and it goes up from there. So these 2 points are my turning points, okay? So if the turning point is higher, so it's talking about this turning point, if it's higher than the nearby points, so these points right here, it's higher in its location. In this general area, it's the highest point. We call that the relative maximum. And then the lower turning point, we call that the relative minimum. And we call these values the extrema. Okay. Now let's talk about this last bullet point. Turning points define where a function is increasing or decreasing. Now, I want you guys to pay attention to the domain. When we're talking about increasing or decreasing, we're looking at the domain, meaning we're looking at the x values, okay? So let's look at this graph over here. I'm just going to give you an example. Let's say I want you guys to write this down. Let's label this first turning point. Let's say that it is at -1, 3. Let's say that that first point is at -1, 3. And let's label this turning point as 3, -3. Okay, so let's talk about where this function is increasing. And you need to pay attention to the domain, the x values only. We're not talking about the y values. So guys, let's look at the graph over here. Way from down here, it's increasing. And it stops increasing right here. What is the x value right here? -1. So that means it is increasing from -infinity all the way to -1 to that first turning point, okay? Let's still talk about increasing parts. Where does it start increasing again? At 3, -3. At this turning point right here, it starts increasing at the x value 3. So it picks back up again at 3, and then it goes up forever. So those are the intervals at which they increase. And you just pay attention to the x values, okay? All right, now let's talk about the decreasing intervals. Where is it decreasing? Between what numbers?
-3 and 3.
Ooh,
-3.
we have to pay attention to the x values because we're looking at domain. Yep, -1 right here and 3. That's where they're decreasing, okay? So between -1 and 3 is where it's decreasing. No, you don't look at the y, you look at the domain, the x values, okay? All right, so now that we know what turning points are and how to write the intervals of increasing and decreasing parts, go ahead and work on the next page. Go to the next page. I want y'all to do that top question on page 9. All right, so this is what we graphed in Desmos, and we're going to talk about the relative minimum and maximum. So guys, what is the relative maximum here? It's right here. What did you guys get at this point here? 0.709 and 3.8. Yes? Okay, so this is your relative maximum, this point right here. And our relative minimum is right here. What is that? 3.291 and -303. Okay, so guys, those are your relative maximum and minimum. Now let's talk about the increasing intervals, okay? This graph that we graphed here, this is the equation for the graph. It is increasing starting at -infinity because it's going forever down, right? And it stops right here. What is that x value? 0.709. So 0.709 is where it is increasing from here to here. Yes? Okay. Where else is it increasing? Yes. From right here, and then it goes up from there. So that point, the x value is 3.291. So it is also increasing from 3.291, and then it goes off forever, continuously increasing. All right, now let's do the decreasing interval. Decreasing is this part right here between these 2 points. So from here to here is where the graph is decreasing. That's between the x value 0.709 and 3.291. Is that okay, guys? All right, so that is how you find the increasing and decreasing intervals. All right, so on this page, you guys use Desmos again, and you sketch the graph. A quadratic looks like this. A negative quadratic looks like this. A cubic looks like this. A negative cubic looks like this. 4th degree, negative 4th degree, and then 5th degree looks just like the 3rd degree. And then negative will make it face this way. All right, so you guys need to answer the questions over here. So I'm going to give you guys a moment to read over those questions about these graphs. Okay, so number 1, it says, which of the functions have the same end behavior? When we say end behavior, they're basically talking about the arrows, the direction of the arrows. What is happening as it goes off to infinity? So when you see end behavior, look at the arrows, okay? Are they pointing the same way? Does it have the same behavior? Are they both positive? Are they both negative? So let's look. Which of these functions have the same end behavior on the right side of the graph as the left side of the graph? So here's the right side, and here's the left side. Are they facing the same direction?
Yeah.
Okay, so that means A has the same end behavior for both the left side and the right side. What about B?
Yeah.
Yep, they're both pointing the same direction. What other graphs are facing the same direction? E and F. They have the same end behavior. Both sides of the function are facing the same direction. They're both going up or down. Okay, so guys, what do you notice about the degree? When I say degree, we're looking at these exponents here. What do you notice about the degrees? They're all even, okay? So they are all even degrees. So guys, what can you deduce from this? How does the degree affect the end behavior? Yep, so if it's even, it'll have the same end behavior. And if they're odd, you will have opposite end behavior. Okay, so let's look at C and D. These are odd degrees. It's degree 3. Also, these down here, this is degree 5. Those are odd degrees. Notice the endpoints are facing different directions. The end behaviors are opposites. Okay? All right, I'm going to pause here and let you guys answer the next questions. Okay, so number 4, it says, which of the functions that you identified in number 1 does the end behavior decrease without bound on both sides? So out of A, B, E, and F, which one is decreasing forever? Yep, B and F. They're both facing down, B and F. Okay, now we're going to answer the next question based on number 4. So what is true about the leading coefficient? Yep, they were both negatives. So these ones that are facing down forever, this one right here, this one's facing down forever, and this one's facing down forever. They both have negatives in the front, okay? So they're both negative. Okay, so guys, how does putting a negative, how does the sign of the leading coefficient affect the end behavior? It'll basically make it opposite, right? If it's facing up, then it'll face down. If it's like this, you put a negative in the front, it'll face like this. Okay, the directions change. All right, nice. So now that we know these general rules, let's look at these parts right here. Let's talk about end behavior patterns. Okay, so guys, the leading coefficient is positive, and this is a degree 2. So I'm going to sketch off to the side. What does this look like? Yep, it'll look like this. When the degree is even, they're going to face the same direction. Okay, so let's talk about end behavior. As the x values go towards negative infinity. So guys, as we go this way on the x-axis towards negative infinity, what's happening to the graph? It's going up to infinity. So f of x goes to infinity. Remember, when you see f of x, you can think of this as y. Okay? It's going up. The y values are going up. Okay? Now follow my pin again. As the x values go towards infinity. So follow my pin. As we go this way, what's happening to the graph? It's going up, right? It's going up. So this is also infinity. Okay? You might also see it written as x goes towards both positive and negative infinity, the y value also goes to infinity. You can write it like that as well. Okay? All right, let's look at a different problem. Which one would you guys like me to do out of 1 through 6? Number 6? Let's do number 4. Let's do 4. Let's do an odd one this time. It's negative and it's odd. So it's going to look something like this. Okay, so let's talk about the end behavior. Follow my pen. Let me do a different color. As my x values goes towards negative infinity, we're going this way. What's happening to the graph? It's going up. It increases on this side, so we'll put infinity here. Okay, let's do that again. As the x values goes towards infinity, the positive infinity, as we go this way, what's happening to my graph? It's decreasing, it's going down now. So we'll put negative infinity. That is how you write end behavior. Okay, so I'm going to let you guys finish these examples. Let's make a chart real quick. Okay, so let's do a little sketch. If it's even and positive, it'll look like this. If it's even and negative, it'll look like this. If it's odd and positive, your graph will look like this. And if it's odd and negative, your graph will look like this. So odd, positive, that can be x to the 3, x to the 5, x to the 7th power. If you put negatives in front of those, these are like negative x cubed, negative x to the 5th, negative x to the 7th. Those graphs will look like these, okay? Even, positive is like x squared, x to the 4th, and so on. Negative, when it's even, is negative x squared, negative x to the 4th. Does that make sense, guys?
Yeah.
These are the general graphs that you'll see. Okay, I'm going to do one more example so that you guys can know how to write end behavior. I want to show you guys the format that we use. Okay, guys, this first one right here, let's sketch this. What will it look like? We'll start at 1 and it'll be linear. It'll look something like that. Okay, so what's the degree? Oh, y'all said it, linear, perfect. What's the leading coefficient? Is it positive or negative? Negative. Oh, so I drew this wrong. It should be facing down, sorry. Yep, it should go like this. It's a negative slope. Okay, so the leading coefficient is negative. We're going to put negative. Okay, so guys, this is how you're going to write the end behavior. This is how you write the end behavior. Okay, so as x goes to negative infinity, what is the y value doing? So let me use another color pen. As I go along the x-axis and I go towards the negatives, what's happening to the graph over here? It's going up. So I'm going to put infinity here. Okay, let's do the other side for end behavior. As the x values go towards positive infinity, what happens to the y values? This is how you write end behavior. Follow my pen again. We'll do it again. So follow me. I'm starting at the origin and I'm going this way. I'm going to the right towards infinity. What's happening to the graph? It's going down. So that's negative infinity. That's how you do end behavior. Do you guys need one more example of this? No? Okay. So you guys can now finish all the way till page, you can finish page 12, okay? Where we're talking about end behavior.